So for the box, we want to know what is the effective R out of the box when we are kind of looking at the box from here. So it's very similar to looking at the transistor, let's draw it on the bottom, from the drain of that transistor. So this is going to be very similar. So let's write it with a capital R representing the box. So R out is going to be 1 over the derivative of I out this time instead of ID over the partial derivative of V out, where V in is constant. So we see there's a lot of these things are very similar. It's just the one on the left and also the GM that we've seen before. The GM that we've seen before, usually cadence tools will give us that for every device, but when we have a complex design, we don't know how to extract these parameters unless we have to solve it mathematically. So I'm going to show you a technique of how to extract the R out and the GM of any design that you like. So if I stop for a second, we said that the partial derivative of the current is actually the transconductance, but that's also equivalent of taking an operation point of that current and just moving it around a little bit next to that current. So if we just draw like maybe a very simple graph of I versus VGS. So we can choose any point on this graph, let's say this point right here, and let's say I want to work right. I want to stay in this area of VGS right here. So if I'm in this area, we can say that it's very simple that the GM in that area can just be ID over VGS without the derivative. So that makes things more simple. And here, if I want to measure that, that means that VDS should be 0. So it's like as if we took the derivative already and now we're just linearizing